Okay, so problem 4 says the following questions refer to the figure below. At the start, the switch between points C and D is open as drawn on the figure. The battery is 5 volts. At this time, switch open, the current measured at point A is 5 milliamps, and there is a 3 volt difference between A and B. R2 is larger than R3. Okay, and then we have a series of questions we're going to answer. So right away, what I'm going to want to do is put on my diagram that we have 5 volts throughout the whole circuit, and that IA here at point A is equal to 5 milliamps. Or millivolts. No, milliamps. Right the first time. We also know that there is a 3 volt difference between A and B. So the voltage drop across R1, BA, is going to be 3 volts. Perfect. Okay, so question A says, what is the current at point D? So what we notice is that the switch here is open, which means that there is no current going through this top branch, which means all of the current hits this junction, and because none of it goes upwards, it is all going to continue on through R3 and ultimately through D. So in this case, IA is actually equal to IB and ID so long as that switch is still open, which means IA is equal to IB is equal to ID, which is just still equal to that 5 milliamps we started out with. Okay, so that is the answer to part A. Moving on to part B. What is the voltage between points B and D? So, we know that the voltage drop from A to B across resistor 1 is 3 volts. And now because by the time when we get all the way through the circuit, we need to lose all of our voltage, right? Because at the positive end of the start of our circuit and the negative end, the end of our circuit, the total difference between those two spots is 5 volts. Which means because across R1 we lose 3 volts, we need to lose the rest of it after R3, which means VBD is going to be 2 volts. Okay, moving on to part C. What is the voltage between points B and C? So in this case, we're still talking about the switch being open, which means there's no current flowing up through the top portion. Because there's no current going through there, that means there is no chance for us to lose any energy across this resistor, which means the voltage at point B is going to be the same at the point C. It means the potential between them, points BC, is 0. There's 0 volts across them. Okay, so moving on to part D. What is the effective resistance of the circuit? So there are actually other ways to solve for effective resistance, or equivalent resistance, as we'll probably call it next week. But in this case, we could just look at the circuit as if it is just one potential, one current, and one resistor, called that equivalent or effective resistance. And so, because we only have one voltage, and we know that that current we have is the same current throughout the entire resistor, we can actually just use those values, that 5 volts and that 5 milliamps, to solve for our total effective resistance. So to do that, I'm going to divide both sides by I, which will leave us with R equivalent is equal to the voltage divided by the current. So we have 5 volts divided by 5 milliamps. And this will get us 1,000 ohms, or we can convert that to 1 kilo ohm. And that is the effective resistance of our circuit. So if we broke this down and simplified it so that we could instead look at this as if it was only one resistor instead of 3, or really 2 in this case because the switch is still open, this is what we would have. Okay, And so one last part E. If the switch is closed, explain what happens to the current at point A. You do not need to do any calculations. Okay, so in this case, if we closed up the circuit, what we would actually find is that the current at point A would increase. And so we could do this using an equation and actually solve for the new value that it would increase by. But we're not going to do that because we really haven't gone into calculating equivalent resistances and working with circuits in that way. Instead, you could think of this as if you were plugging in another appliance in conjunction with R3, right? So we had maybe one light bulb as R3, and we decided to plug in another light bulb in that same place. So we had the same potential across those two things. What happens is we're going to need to actually draw more current to support that. So what's going to happen is at point A, we now have more current to handle the second appliance, the second light. And we'll actually have an actual like quantitative value that we can do this with if we were to do this problem next week and find the equivalent resistance of the whole circuit and calculate out what I through R3, I through R2. But that's for next week, and this will suffice for now. Okay, so that does it for problem 4.